Hey.
Hey.
All right. Hello and welcome.
All right. Hello. Welcome, everybody. My name's Andy. I'm employee, curriculum developer, and designer here at Brown Dog Gadgets.
You got it.
I don't often do these live streams, but here I am introducing a project that I have a special sort of enthusiasm for.
You got it.
Yeah.
I'm here too.
Pete's there. Yep.
Yeah.
Fearless
Cool.
producer Pete.
Sure.
Yeah, so what we're going to be talking about today and what we're going to be taking a look at is a new product that we are going to be offering on our website and whatnot that kind of seeks to pick apart underwater or aquatic robotics.
Yeah.
This project was originally brought to us as an idea from an educator at the Door County Maritime Museum, who was teaching an aquatic robotics competition group. There are several of them out there. Not sure if I can mention them all by name. However, they do in fact kind of have a yearly challenge, these robotics groups, and students and participants will develop an underwater robot, or an ROV, remote operated vehicle, to address these challenges. And as a person who, prior to working here, had worked in that capacity as a coach and as an instructor in one of these programs, I kind of noticed that a lot of the why and the how of the circuitry in this program was pretty thinly explained. And so we were approached at a convention by this educator from the Door County Maritime Museum, and they actually kind of had the same opinion and were seeking out a paper circuits version of that same circuitry. And although one didn't really exist, I kind of had a plan for how to make this happen, having done something similar in my own groups for the same reasons years before working for Brown Dog Gadgets. And so we have what eventually has come to be known as the flatfish. And the flatfish is indeed flat, and it is like a fish, intended for underwater sort of use, or in our case just sort of like a metaphoric underwater use. The real deal we have over here, in case anybody's unaware, ROVs, remote operated vehicles, are little underwater robots. And although that sounds like a pretty complicated thing, it's actually a pretty approachable sort of project for kids. And in this case, though, there are some hurdles. We have a long tether because what we are trying to operate is going to need to go down to the depths, and along with it have electricity routed to things that use that electricity, namely two thrusters on the side and one that's mounted and oriented vertically. And we also have a voltage source for the real ROV, and we have a control box. And when we have it all together, we can rotate motors from topside on a dock or on a boat, and cause those outcomes to happen down at our ROV. And essentially, this little contraption allows for us to explore environments that our human bodies are not always so capable of exploring. So it lets us go down to where we either cannot or don't really want to go ourselves. That said, there's all this wire, and although the circuitry is really simple, for some reason the length of wire and the level of understanding of simple circuitry, they butt heads with one another. And at a certain point, I think that this project, although approachable for kids, sometimes gets a little bit into the weeds with the understanding of how the circuitry works, why we make some of the choices for control elements within our control box, and how it all works together to give ourselves the outcome that goes from our voltage source to the control box to the thing that we're trying to control underwater. So to help students understand a little bit more of that circuitry, we developed a flatfish. And the flatfish, like I said, flat, designed to illustrate something that goes underwater, thus the flatfish. And it's really just a really sort of involved, ambitious paper circuits project. in this case, it's actually 3. So this project will feature this poster template, and all of the work is going to be done on this template. The first project of 1, 2, 3 separate projects is going to really have a couple of different objectives. It's going to be something that helps students understand how electricity in our voltage source gets routed into a control box that has control elements in the form of switches that control outcomes down at an ROV. And so we really kind of tried to use color in this case to show both the negative and positive half of this circuit, but also color that can help students understand which outcomes are being controlled along which paths. So when you get this poster, keep an eye peeled for some of those ways that we've used color to help illustrate some of these details. But basically, we're going to lay down maker tape. So this kit is going to come with and hinge on the use of a conductive tape. Eventually, for these 2 side projects, we're going to use a motor and fan. And that, again, is going to be analogous to our fan and thruster here, our propeller. We use in real ROVs, and then we've got some LEDs. The LEDs are going to be used in our first project to really just get across the idea of voltage to control to outcome. What's controlling what? How is electricity reaching all of these outcomes? We're also going to use it to kind of highlight the differences between controlling something like an LED and what we need to happen in controlling something like a motor. Both use electricity, but both respond to electricity a little bit differently. So we keep it simple for this project up here, again with the objectives of voltage to control to outcome. And then what we do is we take a look at how this setup is maybe a little bit inadequate to achieve the same things that need to happen in a real ROV so that it can go in one direction and the opposite directions, allowing for the real object underwater to go forward as well as backward and right, left, up, and down. So all of that would be a little bit impossible if we set things up the way they are here. And so we set up a need for an improvement. And then we explore that improvement over here in these 2 separate projects. And these really explain why some of the choices are made with regards to switch types and wiring that's used in a typical ROV control box. Okay, so again, kit contents are going to include some Velcro dots that will allow for us to attach a motor here and here, allowing for it to spin freely for our own observation. We've got our 2 motor fan components there. We've got our maker tape. This is going to be powered by 2 AAA batteries, and I'm also going to utilize, like I said before, some LEDs. So rather than spend a whole ton of time making all of these maker tape pathways, we're just going to do the old cooking show reveal. I'm going to get these components out of the way and replace things with a finished version so that we can see how it operates, what it looks like when it's finished, maybe some things for our avid watchers of this stream, because some of the connections and pathway strategies that we use are a little bit different than you've probably seen in previous projects. But here we have a completed flatfish, and as you can see, we've got a lot of these maker tape pathways, and if you can trace on a line with a marker and use a scissors, you can trace on these pathways and snip the paths as needed with this conductive tape. We're going to overlap at points where the direction changes. But with this all set up, I'm going to connect our voltage source right where it's pictured. In this case, red to red, black to black. So our negative path, if we follow it with our finger, is going to come down here. It's going to be routed into our control box, and it's going to split off into these different directions. This particular direction is going to be a separate path that eventually leads to this outcome at the ROV. There's a gap which allows for us to control that gap on and off. The gaps create open and closed circuits. Open circuits are on, closed circuits are, open circuits are off and closed circuits are on. And in this case, the mechanical bit allows for us to control that gap. So with power routed in and a path that goes potentially to this item, it's going to come back this way and return to the voltage source. So we start to understand that, for every outcome, we're going to need to have some electricity that's coming in from a voltage source out to that outcome thing that's going to use the electricity and come back to that same voltage source. You'll notice I have omitted one particular type of path. You'll also see a couple of these paths that when I hold them, or when I kind of angle this up, you can see that the middle portion of this path is not, there it is, yeah, all right, right in there. There's a loop where the middle portion of that particular path is actually not pressed down. It's jumping over the wire below. And that's important, not only for some of this circuitry that explains the switch choices we make in an ROV control scenario, but it's just going to allow for us to kind of avoid contact with this path and these pathway parts controlling that outcome. So that can lead to some shorts in our circuit. And the way we avoid it is with these jumped pathways. So I'll show you real quickly how we're going to create one of those. And this jumped path is marked on the template. They all are. Here's another one. One here, and also one here. So because all the rest of these pathways are pretty straightforward, tracing, laying tape on the line where we indicate it, this one's a little bit different. And so I'll show you firsthand. So we are going to start with a piece of maker tape. We're going to remove it. And to be completely honest, what I typically will do is either use an object, pen, pencil. I attach at this point. I kind of let that connect over here, and I never press that middle part down. So I kind of, a pencil is real nice to use for that form, but essentially what we're trying to do is just go from this contact point over this one to contact right here. I think I actually cut my tape just a little bit too short, but what's nice about this maker tape is that we don't have to take that off, this pathway off, remeasure it or anything. We can just patch right on top and extend that pathway because of the way that the tape is structured. So now that we have a fully complete path from here over here through the LED and back to the voltage source, save for our gap, we can control that outcome. And in this case, we can see very clearly now I can sit topside, dry on a dock or on a boat, and I can use a control element in my control box that allows for me to control something that's happening underwater after a big long tether. And that's this tether right here. So that said, with that path complete, we can also control this, and every time I press this down, it turns on, and every time I lift off, it doesn't. It turns off. So we can essentially pulse at these two outcomes, and the same thing happens up here with this one. Now you'll notice that there are two switches up here, but the only thing they're really doing, the only outcomes I can generate with LEDs and these simple switches are just ons and offs. And that works fine if we're just turning lights on and off, but what we're going to ultimately be controlling are motors that not only need to spin one way, but also need to spin the opposite way. And so the way we have this wired, although it helps to clarify power coming in to a control box, controlling outcomes, it falls short in what we actually need to do with a real ROV. And that's where these different switch setups come in. And so you'll see that it's very easy for us to go from one of these projects to the other. One thing that you'll notice, these other projects, both the one that we just kind of highlighted and these, there's a paper switch bank up here at the top of a brand new flatfish poster, and this is all you're going to need: scissors, switch bank, and your maker tape, and you'll be able to create all of the different switches that are going to be involved, not only down here but also at these improvement switches. So the first way that we can improve upon switches within our control box when it relates to motors is by using something called a double pole double throw switch, and that's what these are. In a real ROV, they allow for me to turn these motors on, but when I push forward, I get one direction of motion over here, and when I pull backwards on the same lever, it goes the opposite way. And the way that's actually happening is something that used to be a little bit more DIY and fully wired yourself when you were creating something like this. But in this particular ROV competitions program, things got a little bit tidier in the control box. Everything got put into a circuit board, and so we don't really get to see a lot of the why of these switches working. And the truth is, what we have here is called a double pole double throw switch. And the way things work, and we have curriculum that is hosted on our curriculum and instruction page on Dozuki, that not only has all of the procedures and videos for assembly, but for each of these projects, there are also sort of assessment tools, ways that participants can map out how electricity is flowing. And in this case, with the double pole double throw switch, when we engage the switch, the mechanics of the switch here, and contact these, I gotta bring power in, don't I?
Yeah.
That is always needed. And so again, really quick, simple, we just keep these little pieces of maker tape to the ends of our battery pack leads just to connect and bring power into this separate circuit. We've got a motor now mounted by Velcro so that we can move it over to this and keep it stable in each position so that we can see the direction of motion without kind of like, worrying about what our hands are doing. But if we take a look at the way this circuitry is set up and structured, we've got power coming in. We've got, on this side, we've got two conductive stripes. On the opposite side, we've got two conductive stripes. We've got two stable pathways here. Red motor wire A, that's where we connect that red wire. Black motor wire B label down here, connected to the black wire. This arrangement stays stable and is never going to change because we can't swim down to ROVs and while we're operating them go down and cross wires, right? So this is going to never change. But while this is stable, we can activate different routes through the circuitry that will allow for the motor to spin one direction and its opposite direction. So when I push this particular switch forward and make these contact points contact the circuitry, the electricity is actually flowing here, contacting the underside of this connection point, coming up here, and contacting our outcome in one particular order. Now, when I pull this back, what we're actually contacting is the opposite because we have crossed these wires. So just by creating this cross, right, with a jumped wire in between and a mechanical bit that allows for contact to happen either in this way or its opposite way relative to the cross, we can get electricity to flow through this whole system in one direction en route to the motor and then its opposite direction. And the effect is really just the spin that we need, the variety of spin that we need in order to really make this thing controllable.
And you know what Josh would say?
What's
Josh
that?
would say, reverse the polarity.
Reverse the polarity.
That's what you're doing.
It is. It
Yeah.
is. We're reversing the polarity. And, you know, when we talk about LEDs, LEDs are an electrical component that only allow for electricity to go through them in one direction. So all we can really do is turn them on and off. There are bidirectional LEDs. They're kind of a...
Well, the D stands for diode.
It is.
And yeah, only one current can only go through in one way.
Yeah, that's that whole family
Yeah.
of components really kind of limits the way electricity can go in to them and out of them. If we were to try this component with this switch and do this, one of the outcomes would work
Right.
and turn on the LED, but the opposite one would try to send electricity into a component that pretty much only has an indoor and an outdoor. These components are kind of like swinging doors, right? Like you can go into them one way and you can also go into them the opposite way. And the effect here, by reversing the polarity in relation to a motor, a component that responds to electricity being sent into it in opposite polarities, is the opposite motion. And that is really useful when we're trying to either fly something or, create the spin that drives it forward underwater. So we've got one project here. Again, the objectives: power, control box, outcome. See some limitations which motivate an understanding of the improvements made at these two switches with the double pole, double throw switch. And that explains why this switch is a good fit for this component and this desired outcome. We also have these other switches up here on our real control box, and these are push button switches, and they actually, scoot this over here into view. This is our vertical thruster, and this allows for us to go up and down. One of these push button switches makes it go up, one of it reverses the polarity and makes it go down, spinning the opposite way. So to make this happen, again, in paper circuit realm, really kind of has to do with that critical shape and feature of an X. And we see that X again here, again with a jumped wire, this one right here being the jumped wire. But we see that familiar arrangement of conductive pathways. And in this case, when we disconnect the power from this switch and we reconnect it over here, and we move our motor in the same way over to this new circuit. These are just two push button switches. They are momentarily open, and that means that momentary closed, sorry. It means in their normal state, they are open. In other words, they're not contacting down below and they're not closing the circuit. And in their activated state, in other words, you're pushing on them, they are momentarily closed. And that closed circuit is one that is on. And so here we have voltage coming in, splitting off to two different outcomes that feed into a cross. And depending upon which one of these pathways we activate, we can get one polarity and the opposite polarity just by pushing on these switches. So, that said, we, through paper circuitry, have an opportunity to really kind of understand some of the core ideas, some of the nuts and bolts of what it takes to create an aquatic robot, and a remote operated vehicle, or even an AUV, an autonomous underwater vehicle. A lot of that, circuitry may be relevant, although autonomous is not going to have your control. It's going to go by itself. So, that said, we've got this brand new project. You know what the kit contents are. some of the context for how it came about, what it explains, and in terms of who this might be appropriate for. Maybe you are somebody who's working in the Sea Perch program or the MATE program or any of the other aquatic robotics competition programs, and you're looking for something that might be able to take some of the core ideas that are maybe thinly sort of explained in their direct curriculum and just kind of expand on that. Maybe you're a landlocked teacher who wants to get their kids into aquatic robotics, but you might not have access to either a pool or a body of water where you can test the real thing. This is a great way to kind of get your feet wet, so to speak, while keeping them dry. Even if you are just teaching some bit of circuitry that, broadly speaking, has voltage going into a control box and has outcomes that need to be controlled. A lot of these things are really still useful and relevant ideas for that kind of circuitry, for anything from remote control vehicles to simple telerobots, that type of thing. This is just a broad and fun sort of ambitious paper circuitry project, and we're excited to launch it and hope that you consider it and take a look at it. Aside from that, that's about it.
Yeah. And I think we showed the guides, and those are all at Learn, browndoggadgets.com.
Yeah. So each of those,
Flatfish.
yeah, totally. Those four projects, they all have a sort of condensed video bit of instruction, but also photographed instruction, and like I said before, support documents that'll allow for you to print out some printables and check for comprehension and understanding of some of the things that we're really trying to drive home about this. So fully supported by curriculum, fully supported by assessment documents, and hopefully this can either give you an opportunity to bring aquatic robotics into your classroom when you might not think it's possible, or give you a way to extend the things that you're already doing in that classroom.
Yeah, and as always, if you have questions about this or interested in it, whatever, hit us up, email help@browndoggadgets.com, or you can check our website, get our phone number, give us a call. Happy to kind of answer any questions and walk through things with you.
Yeah. And I think these are going to be available in a variety of different sizes depending upon your group size.
Yeah.
I think we're doing like 5 packs of them so that you can kind of tailor, multiples of 5 to address the needs of whatever group size you may have.
Mm-hmm.
Yep.
Cool.
So, yeah.
That's a great overview, Andy. I think it's an exciting new project, really different than a lot of stuff we've done before as far as the scope and what it relates to, which is really cool.
Thanks, man.
Yeah.
I'm excited about it. It was like, I worked for years prior to working here at a science and technology museum, and it was one of my favorite sort of programs to run with kids, because
Definitely.
it really does feel like they created something that they didn't expect that they'd be able to create themselves, and it provides an opportunity for all kinds of like just adjustment and observation and fine-tuning, which are all just like key practices in engineering.
We always talk about like tools being an extension to what humans can do, our own capabilities, and I mean that's what this is. It allows to kind of you to go into the sea or whatever. I know there's like a camera mount on there too, right?
Yep.
So you can actually record.
Yeah. We got 2 of them. We've got a live cam.
Oh, okay.
On this one, we've got this guy's a live
cool.
cam, so that is used mostly for navigation, and then we've got one that'll record. I used to use a GoPro, and now I've got a Insta360, so we can just kind of capture 360 degrees of what's going on and record it.
Super cool.
But it's one of those things that I think so many people at first glance and first consideration, they're like, wow, an underwater robot? Circuitry isn't made for underwater. That has to be impossible. I can't do it. But it's really actually a lot more approachable than you think. And it's the type of project that I think, can really spark an interest in this and really kind of like, redefine what kids think they can and can't do.
Yeah, nice. Well, I think that's all we got for today with this, and I believe Amanda's back next Tuesday, and we're doing another literacy thing, so combining sort of literacy with some paper circuitry stuff. So
Sweet.
that's what we got.
Yeah, all that stuff that she's putting up with regards to literacy connections are really cool.
It's very cool. Yeah, we're really branching out, I think, to all sorts of stuff. So
Yep.
yeah, I think
All
that's
right.
it then.
Well, thanks for giving me your time, everybody.
All right.
Take care.
Thanks for watching. Please visit browndoggadgets.com for parts, projects, and curriculum. Follow us on social media @BrownDogGadgets. We'll see you next time.